Okay. Do you see my slides?
Yeah.
Okay. And you can hear me well?
Yeah, fine.
Okay. So let me start. So first, let me thank the organizers for the invitation. So I will be presenting SMEFT Atlas of delta F equal to 2 transitions, which is based on the work done with Andrew Boras, Christoph Bobeth, and Jason Abisher. And this paper came out in September 2020. So since this is only 20-minute talk, it will be a very brief overview of this rather long paper. So I think this I can skip the SMEFT introduction to SMEFT. It can be easily skipped because I think it's already been discussed many times in the conference. Okay, but let me directly go to the general strategy that we follow in all kind of SMEFT analysis. So we have a new physics model at some high scale, let's say lambda. We can match this model to SMEFT, and it gives us some number of operators, higher dimensional operators, which of course depend on the model. Then we have to run these operators down to the electroweak scale using the RG equations, which are calculated by the group of Nish, Manohar, and all. At the electroweak scale, we have to match the SMEFT onto weak effective theory because electroweak symmetry is broken, and then we have a totally new effective theory with a different symmetry. So we have a LSM plus a series of weak effective theory operators. Finally, we have to run down to very low scales like mass of bottom quark or tau lepton. This depends on the observables, okay, at which scale we want to stop. So this is the general strategy that I will be using. Okay, so the goal of the present work is to provide a general master formula of delta F equal to 2 observables in terms of SMEFT Wilson coefficient at the new physics scale. So this will facilitate the model independent studies of delta F equal to 2 observables. So these are the ingredients that go into this master formula. So from low energy to electroweak scale, we use two loop running calculated by Buras, Jagger, and Orban and Misiak in these two papers. For one loop matching of SMEFT onto wet, we use Denkens and Stoffer's calculation. And for one loop RG running, these standard 3 papers by this group. Okay, so let us briefly look at the observables that we are interested. So basically, we are interested in the mass differences for B and K mesons, which are given by these formulas. So the quantity that we want to calculate is basically M12, which is a standard model part and BSM part. Here the index ij is the flavor index. So depending upon the observable for K, BS, and BD, it has this structure DS, SP, and DB. It is well known that the standard model part is given by these box diagrams, and BSM contribution can be expressed in terms of series of effective operators. So here the effective operators they belong to weak effective theory and a suitable basis. So what are the bases that we use in SMEFT in weak effective theory? So in this work, basically, I will be using two bases, BMU basis, which is due to Buras, Misiak, and Orban, and JMS basis. The first basis, it has these 5 operators plus the chirality flipped ones. So in total, we have 8 operators. This basis is very good for wet running because these anomalous dimensions are calculated in this basis by these people. Then the JMS basis is good for one loop matching onto of wet onto SMEFT, done by Peter Stoffer and Denkens. So okay. So once you have, let's say we have the low energy Wilson coefficients in the BMU basis at the low scale, we can run them up to the electroweak scale using the BMU RG equations. At the electroweak scale, we translate them to the JMS basis because the matching of SMEFT onto wet is done in the JMS basis. So to make this connection of wet to SMEFT, it's good to make a transition to JMS basis at the electroweak scale. So we can reach here. Now, to reach here, to go to SMEFT, we have to do matching of SMEFT to wet. So let us look at the matching of wet onto SMEFT for the operators for which delta F equal to 2 observables, on which delta F equal to 2 observables depend. So at the tree level, we have only these 5 operators given here in this set B, which are relevant. And tree level matching of wet onto SMEFT is given by these equations. So you can see, so this is done in the JMS basis. So you can see there's no tree level matching to the scalar operators, which is very interesting. So at tree level, you will not generate the scalar operators. Okay, in general, you can express the matching by this general formula. So first term is given by the tree level matching, which is just represented here. And then we have this one loop matching, and in one loop matching, many more Wilson coefficients will come into play. I will come to this point later in my talk. Okay, so we are here at this point. Now to reach to the new physics scale, we have to perform running from electroweak scale to the new physics scale, lambda. So let us look at the running. So RG running of this Wilson coefficient depend on the standard model couplings like Yukawa couplings and gauge couplings. So first, let us look at the Yukawa dependence. So this is the one example of the solution for the RGs for QQ1 operator. So on the left-hand side, I have a Wilson coefficient of QQ1 at electroweak scale. And on the right-hand side, I have the Wilson coefficients at the new physics scale. So all these Wilson coefficients are at the new physics scale. So you can see that if we have a operator like QQ1 with flavor structure KJIJ, it can give rise to operator IJIJ at the electroweak scale. So the flavor, notice the flavor structure, which is not exactly IJIJ at the new physics scale, but at the electroweak scale, you can generate through the CKM mixings represented by lambda. So this is very interesting that through Yukawa running, you can generate the relevant Wilson coefficient from an entirely different flavor structure at the new physics scale. So this Yukawa dependent running is the flavor dependent. Then if we look at the running of the same operator QQ1 due to the gauge couplings. So this you see QQ1 can mix with QQ1 and 3 and the flavor structure is same at new physics scale and the electroweak scale. So this running is doesn't depend on the flavors. So similarly, we can have the RG running for other 4 operators which are relevant at the electroweak scale in SMEFT. Okay, so let us look at a complete picture of the running. This running, which I gave just one example. So in this chart, on the top, I have Wilson coefficients at scale lambda, and here at the bottom, I have Wilson coefficient at electroweak scale. Okay, and the different lines, black, green, and red, they represent the different couplings. For example, the black lines represent the Yukawa couplings, red lines represent strong couplings, and green lines represent the weak couplings. So as I explained in previous slide, the running depends on various standard model couplings. So here I'm showing you the mixing pattern due to different kind of couplings. So on the top chart, on this chart, I have only the operator mixing in which if you start with ij flavor at the new physics scale, you end up with ij flavor. Okay, so the flavor structure remains same. So this is mainly due to the gauge couplings, red and green lines. You can also have the black lines due to Yukawas, which preserve the flavor structure. Then on this chart, I have the mixing pattern due to only the Yukawa couplings. So here you can see I can have different, entirely different flavors from IJ, for example, IK, IJ operator, QQ1. It can mix with the IJ, QQ1 operator. Okay, so if you start with the QQ1 operator at new physics scale with this flavor structure, you end up with the flavor structure relevant for the delta equal to 2 processes. Okay, let's continue. So to summarize, at the tree level, only these 5 operators are relevant for delta equal to 2 processes with flavor structure IJ. And when you include one loop running, then many more operators will come into play, and with the very complicated flavor structure. Okay, and due to one loop matching, as I said, we also take into account one loop matching at the electric weak scale. This just adds one additional operator to this set B prime. So at the new physics scale, a large number of SMEFT operators can contribute to delta equal to 2 observables. So the goal is to have a general master formula in terms of all these operators, including the RG running effects at various stages and one loop matching at the electric scale. Okay, so this is the master formula. So basically, to calculate delta ms, the mass difference, we need M12. M12 can be written as so here we pull out the delta M experiment. Then here you are left with Pij times Ca, which are the Wilson coefficients. So at the new physics scale, we calculate these Pij factors. Then it will give us delta M2 divided by delta M experiment, which we defined sigma. So this sigma is basically percentage new physics contribution to M12. Okay, notice one thing here. I have a small c and bigger c. The big capital C is just you can think of it as a c divided by lambda scale. So in capital C, I have absorbed the scale new physics scale. Okay, and here you have to sum over all possible operators. A is the sum over all possible operators, which I showed in previous slide, in this slide. So that can be due to matching or running or all sorts of effects. Okay, so this is one example of how the master formula looks like for the QQ1 contribution. So obviously the leading contribution comes to a BS mixing comes from QQ1 2323 operator. You can see the coefficient, which is very large. Then next to leading contribution is this QQ1 with flavor structure 2333. So this is clearly due to the Yukawa couplings, as I explained. Yukawa couplings can give you flavor dependent RG running. But as compared to the leading term, this coefficient is small, but it can happen that you can have a new physics model which in which you do not generate this operator, the first operator. Then the leading contribution will be given by this. Similarly, for BD and K, we can have similar master formulae. And similarly, we have list of all master formulae for various operators, which are very long. So that's why I just show you only one example. So if, for example, if we have a sigma equal to 0.1, that means 10% new physics contribution. So here, if we look at the typical bound on the first operator, QQ1, to constrain the new physics contribution under 10%, this Wilson coefficient has to be less than this, which is a rather strong bound. Similarly, on the second operator, QQ1 with flavor structure 2333, we get this bound, okay, by imposing a similar constraint that new physics should be under 10%. So you can see that there are very interesting correlations. So first correlation you see here that this operator QQ1 with flavor structure 2333, which is a delta F equal to 1, basically. Delta F equal to 1 operator, it can contribute to delta F equal to 2 observables. So in this way, you can correlate correlated different kind of observables through this RG effects. Okay, so let me come to the summary. Given the non-observation of new states at the LSC, SMEFT provides a very convenient framework to parameterize the new physics effects. So we have presented a master formulae for delta F equal to 2 observables at the new physics scale, taking into account RG effects in SMEFT, which are flavor dependent, and this is very interesting, and it can lead to very interesting correlations of delta F equal to observables to other sectors, for example, delta F equal to one sector. Okay, thank you very much for your attention.
Okay, thanks, Jacky. Do we have any questions? Susanna.
Thank you, Tyler. I have a question about the scalar operators. So in the very beginning, you mentioned that scalar operators cannot be generated at tree level, but they could at loop level, correct?
No, if you see in my list here, yeah, so even at loop level means including the one loop RG effects or one loop matching, you do not generate these operators.
In SMEFT, right? I mean, in SMEFT, you don't generate them because they violate hypercharge, so you cannot.
Yeah,
but
yeah, exactly. So even
below the weak scale, the electroweak symmetry is broken, right? So I would expect that at the one loop level or in general, you could have matching contributions onto the scalar operators in left, so in weak effective theory.
Yeah, you mean from one loop matching of SMEFT onto wet?
Exactly. Mm-hmm.
Yeah, but no, I think we don't. Still, we haven't. We don't generate these operators. So all that. So at tree level, you have these operators, the set B, which will generate only the vector operators, and then at one loop, all these operators come into play, and none of them generate scalar operators. And when you add one loop matching, the only thing that is new is CUW operator, which again doesn't generate the scalar operators.
Contribution.
Yeah, so we didn't find.
Do you know the generic reason? I don't know that. So there must be really a physical reason.
Yeah, I think the in the one loop running, clearly it violates the hypercharge. So I think you will not generate it. So in one loop matching, in principle, you can generate it, but yeah, I can't see.
Hypercharge is broken in BS mixing, right? So I don't really see how that could protect me from generating hypercharge violating operators. So flavor-wise, this would fit. So there are matching contributions. So I can draw diagrams, but I don't know the reason why you don't generate scalar structures.
Yeah, I know that at dimension 8 you can generate these operators, dimension 8 level. So maybe you can maybe those contributions correspond to one loop matching, but I haven't looked into it this thing in detail.
Okay, thanks.
Thanks. So I'm gonna hop on to Jason now so that we catch up a little bit more. Thanks for your talk, Jacky.
Thank you.